Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. Today we are going to discuss about the module Principles and Instrumentation, that is NMR spectroscopy, from the paper Characterization of Materials 1. After studying this module, you should be able to understand the principles and instrumentations for NMR spectroscopy. We will be studying about the relaxation processes, principles of NMR spectroscopy, and the instrumentation regarding NMR spectroscopy. So the first is principles and instrumentation NMR spectroscopy. In the past 50 years, NMR, that is nuclear magnetic resonance, has developed along with other technical advancements such as highly efficient computers capable of quick Fourier transform, efficient spectrometer control, and stable high field superconducting magnets. Until past 1.5 decade ago, NMR was very rarely used for solid materials. However, the improvements in magnetic angle spinning, that is MAS, induced spectral resolutions has made NMR an important tool for probing the local structure of solid materials. NMR provides spatial information by applying magnetic field gradients. This module will offer the basics of nuclear magneton resonance spectroscopy along with the brief review of recent advances. So let's discuss about it. So students, let us discuss about the principle of NMR spectroscopy. Since nucleus of every element is charged, therefore when spins of protons and neutrons within the nuclei do not get paired, then small spin of nucleus creates a magnetic dipole along axis of the spin. The magnitude of this dipole is a basic property of nucleus and is described as nuclear magneton moment. Symmetry in charge distribution within nucleus is a function of internal structure and shape. For symmetrical distribution, for example, 1s hydrogen orbital, for it, the spin angular momentum number is I, which is equal to 1 by 2. Thus, the magnetic moment, example 1s hydrogen orbital, and angular momentum is 1 by 2, that is J is equal to 1 by 2. Thus, the magnetic moment magnitude at a particular direction can have two equal and opposite values. The presence of magnetic field H along the z direction may be considered as aligned either with the field, that is Iz is equal to minus half, or against it, that is I is equal to minus half. Analogous to the compass needle in the Earth's magnetic field, favorable energy density with the applied magnetic field strength, that is H, or delta E is equal to gamma H cut into H, where H cut is equal to H upon 2 pi. H is the Planck's constant and gamma is the constant of proportionality, and it depends upon the type of nucleus, for example 1H, 13C and 1N, etc. Similarly, nuclei that possess non-spherical charge distribution like a hydrogenal orbital, that is hydrogen 3d orbital, have higher spin numbers, for example 12 boron, 12b, 17n and so on. The application of external magnetic field B leads to the alignment of magnetic dipoles of NMR active nuclei in S, where S is equal to J plus 1. that is 2j plus 1, orientation stir spin states relative to the field, which is given by the following expression. The alignment is limited by quantum mechanics and the corresponding nucleus process at a frequency n, which is given as nu is equal to mu beta n beta naught upon hi, where mu represents the magnetic moment of the nucleus and beta n is the nuclear magnetron constant. So the magneto-gyric ratio, that is gamma, can be expressed as gamma is equal to 2 pi mu beta n into hi. So equation 1 becomes nu is equal to gamma times b naught by 2 pi. Now one can make the following conclusion which can be reached and are as follows. The magnetic moment, that is mu, is directly controlling the sensitivity of NMR experiment, such that the sensitivity increases with a corresponding increase in the value of mu. Moreover, the next point is the local field experienced by the nucleus is B naught, which is not equal to B. It is affected by various electronic factors, that is mainly induction and anisotropy, which controls the local density of electrons around the nucleus. The next is inherent frequency of a nucleus is constant, whereas its precessional frequency versus dependent on B naught. So different spin states have different energy levels where RF frequency photons can bridge delta E's between these levels. The promotion among spin states, which is shown in this figure, occurs when incident frequency exactly matches the resonance frequency, that is nu. Additionally, the excited nuclei can also relax to lower spin states. This is called spin filling. Excited nuclei can relax through several mechanisms. The most frequent among these two are spin lattice relaxation and spin-spin relaxation, both of which are non-electromagnetic vector, such as a molecule involves transfer of energy from the excited state to ground state. Spin lattice relaxation involves transfer of energy from excited nucleus to an electromagnetic vector, such as molecule of polar solvent or intramolecular group experiencing vibrational rotational processes. On the other hand, spin relaxation involves that extra energy to be similarly relaxed nucleus. In addition to this, the excess energy may also be re-emitted by the excited nucleus. The effective excitation is governed by the rate of relaxation, and it increases the mean half-life of the relaxation and the result in sharp spectral lines. Now comes relaxation process. The Boltzmann distribution describes the thermal equilibrium energy level distribution in materials where the interaction among nuclei are weak. The thermal equilibrium is reached through exchanging energy with the surrounding or the lattice. The time T1 required to reach thermal equilibrium is characteristic of the material and is termed as spin lattice relaxation time. Let us consider the behavior of the macroscopic magnetization Mz, which is the vector sum of the nuclear dipole component along the polarizing field Bz. The achievements of the equilibrium longitudinal magnetization, that is m naught at t is equal to 0,
yields mzt is equal to m naught times 1 minus exponential minus 1 by t1. To achieve the initial state, a 90-degree pulse is applied and mzt is experimentally measured from the signal following a second 90-degree phase. Therefore, the RF pulse sequence 90% to t to 90 degrees produce a signal whose amplitude is given by Vr is equal to V naught 1 minus e to power minus tau by t1, and its measurement as a function of tau leads to the determination of t1. So the stimulated transitions across the nuclear spin energy levels are required in spin lattice relaxation. These transitions are the result of fluctuating interaction which are caused by local magnetic field at Larmor frequency.
An alternate equilibrium condition for nuclear magnetization requires a zero transverse magnetization which is resembled by MXY. The transverse magnetization can be produced by applying a coherent electromagnetic radiation at a resonant frequency, example a 90-degree pulse. The maximum magnitude of transverse magnetization is equal to the equilibrium magnitude of the original Z component. So, various local fields may be generated by either external, such as any inhomogeneity in Bz, that is, magnetic field in Z direction, or internal, such as field caused by nearby nuclear dipoles factors, which results in variations in precessional frequencies throughout the sample. So this result in loss of transverse coherence after a characteristic relaxation time T2, which is known as spin-spin or transverse relaxation time. Typically, the magnetization decay in transverse direction is exponential in case of liquids. So measuring MXY with variation in time offers information about the local fields, which is important to study microscopic level structures as well as dynamics of materials.
Now comes instrumentation. The NMR spectrometer, as depicted, applies RF pulse to the sample. RF pulse is basically under investigation. So during the investigation or the experiment, the sample is placed inside a high magnetic field and time in response to its spin after application of pulse is measured. The magnet and probe are central to the working of the equipment, and high magnetic field is critical to the analysis, and the highest commercially available magnetic field is 13.55 Tesla, which is usually employed in high resolution investigations. The standard equipments can generate anywhere between 4.7 to 9.4 K. The magnets are usually prepared from niobium tin or niobium titanium. Must filament were base superconducting solenoid placed within the liquid helium are more common. So, nonetheless, new and improved materials are required to generate still higher magnetic field necessary. A nanoscience and nanotechnology are investigated. Furthermore, the magnetic field must also be homogeneous. High magnetic field results in improved sensitivity by enhancing the Boltzmann factor as well as a resolution by boosting the chemical shift dispersion. But when line broadening is entirely decided by the chemical shift anisotropy, The higher magnetic fields adversely affect the powder line widths even though it reduces the thermo order quadrupole effects. The receptivity R is expected and determined to determine how readily the different nuclei can be observed. So, R x, where x is the subscript, is equal to gamma cube with x as a subscript times Cx into Ix plus 1. In case of solids, the RF transmitter should produce short in microseconds and intense, that is minus 1 kilowatt pulses. The block vector model is used in rotating reference frame to model the effect of these pulses on a spin 1 by 2 nucleus. A pulse of duration t applied precisely at resonance creates a resultant field orthogonal to B naught in the rotating frame of reference, which further leads to a coherent rotation of the magnetization such that it is stepped by an angle theta away from B naught towards the transverse xy direction, with theta p is equal to gamma b1 into Tp. So students, you can see the block diagram showing the essential components of NMR spectrometer. Following the pulse, the magnetization processes freely in B naught bracket at omega naught is gamma B naught and may be used for the inducing a voltage in some nearby coil. The signal is known as free induction decay, that is FID, and the signal to noise ratio, that is SNR, can be improved by coherent addition of NFIDs. Students, you can see the cross-sectional image of the magnet used in NMR spectrometer. In a typical NMR investigation, the specimen is positioned in a coil and introduced in a static magnetic field as shown in figure 4. Due to magnetic field, the nuclear spin get polarized along z-axis, and beside this field, a transverse magnetic field B1 can also be applied along the z-axis, which can be generated by applying an AC current in coil having Larmor frequency, which is given by omega L is equal to gamma n into B naught.
By doping, the resonance frequency of the circuit, which is shown, gets changed by varying capacitance of both the capacitors C and C prime. By matching the impedance of power supply, that is 50 ohms, with that of the rest of the circuit, the maximum power can be retrieved from the power supply. For appreciating effect of B1 on the nuclear spins, it is appropriate to describe a rotating frame of reference that rotates about z-axis at Larmor frequency. So when AC circuit in the coil is switched on and off, the pulsed B1 magnetic field is generated along the x-axis. This field is the sum of two components, a clockwise and another anti-clockwise rotating fields. The components that remain stationary in the rotating reference frame is significant and is considered further. So the spin responds to this pulse by generating a net nuclear magnetization vector to rotate in the direction of the applied field, that is B1. So the rotational angle is affected by on-time fields as well as its magnitude, that is B1.
So students, you can see a diagram showing the resonance circuit for the NMR probe. So a pi by 2 pulse causes a rotation of 90 degree in nuclear magnetization about x-axis down to the y-axis in clockwise direction, and in case of laboratory frame, then the equal or then the equilibrium nuclear magnetization spirals down and around the z-axis to the yz plane. The rotating frame of reference is usual and is useful to describe the behavior of nuclear magnetization in response to the pulse magnetic field. Likewise, a pi pulse rotates the nuclear magnetization vector by 180 degrees. So, if the initial nuclear magnetization was along z axis, then it is rotated down along z-axis. Principle and instrumentation, NQR spectroscopy. So what is NQR spectroscopy? NQR, that is nuclear quadrupole resonance spectroscopy, is widely used technique for studying solid state materials, and it is mostly used to determine the effect of pressure and temperature on nuclear quadrupole resonance signal, and the following describes the instrument and working of NQR. So first is the principle. NQR, that is nuclear quadrupole resonance, exploits the interaction between the electric field gradient, that is Q, and quadrupole moment, that is capital Q, where capital Q displacement of mean distribution of nuclear charge from the spherical symmetry. The non-spherical nucleus is placed in electrical field gradient, and the spinning nucleus may have its axis of spin along the direction of elongation, that is plus q, or compression, that is minus q. In this regard, a particular nucleus can have either plus q or minus q spin, but both is not necessarily to have and is represented by E and small q. So E is the average electric field and Q is the gradient along z axis of the principal axis system. So the energy level distribution is quantized along Q, and the quadrupole coupling constant, which defines the strength of the charge, and the average electric field gradient, that is EQQ, or we can say E square QQ. However, the dimension of Q change in this case. So to detect the NQR signal, the obtained line frequencies are mapped to quadrupole coupling constants, which lead to the direct accumulation of magnitude of nuclear quadrupole coupling constant, that is E capital Q into small q, from line frequencies. So the figure shows the schematic depiction of non-spherical spinning nucleus, that is Q, and its interaction with electric field gradient. So among the available elements in periodic table, as many as 70 of them possess at least one isotope with quadrupole moment capital Q. The elements exhibiting NQR signal are shown in the later slide, and as evident from the figure, several low atomic number elements, example lithium, beryllium, boron, hydrogen, nitrogen, etc., demonstrate NQR activity in all or at least one of their isotopes. Of these elements, nitrogen and chlorine have attached much interest where NQR has been used to determine the resonance properties. Nonetheless, NMR study are difficult to perform. For instance, the NMR analysis of 14 nitrogen, that is the main isotope of nitrogen, suffers due to its quadrupole moment, which causes broad lines in NMR spectrum, and on the other hand, 15N or 15 nitrogen can be readily used in NMR, as it does not exhibit the quadrupole moment. However, it is only 0.4% in nature, making the achievements of resonance rather difficult to detect. In this case, the highly sophisticated computerized techniques such as Fourier transformation used to investigate the resonance. So this figure shows the periodic table showing the elements having quadrupole moment, which we have discussed in the previous slide. But analogous to 14 nitrogen, the isotopes of chlorine both exhibit quadrupole moment, and it includes NMR analysis of these isotopes. And nonetheless, the resonance signal for NQR study are easily depictable in chlorine. So figure which is shown in the next slide hides in NMR and NQR, wherein the energy levels are drawn for a nucleus having a highest quantum number, having a spin quantum number of 3 by 2. As the isotopes of chlorine also have a spin quantum number as 3 by 2, this can also be considered as the energy level diagram for chlorine in NMR and NQR. In NMR, resonance occurs when the energy level splits due to magnetic field. Thus, the resonance is absent in NMR when applied magnetic field is zero. The application of non-zero magnetic field splits the energy level into four, and subsequently a simple type of chlorine, a non-stop magnetic field, splits the energy levels into four, and consecutively a single type of chlorine can undergo several transitions, thereby leading to a broadening of spectral lines in NMR. Additionally, it has short relaxation time. This figure shows the comparative energy level diagram of NMR and NQR for the nuclear spin of 3 by 2. However, in case of NQR, there are two energy levels for a material even when no field is applied. These energy levels are Mi is equal to plus minus half lower one and Mi is equal to plus minus 3 by 2 higher ones, which allow one transition from one type of chlorine in the material. A weak magnetic field splits both these levels, thereby broadening the line, and a minimum of two lines appear for a single type of chlorine. So for correlating with the line frequencies of a particular structure, it is necessary to generate a simple spectrum. Therefore, a magnetic field is usually not applied in NQR experiments unless specific instructions are to be followed. So consecutively, NQR is preferred over NMR to observe resonance signal from the topics having the spin quantum number of 3 by 2.
NQR is performed in solid state materials, whereas high resonance NMR involves liquid or solution state materials. As a result, the averaging effects as observed in high resolution NMR is not present in NQR experiments. Thus, nuclear spin systems, while interacting with electric field gradient, is influenced by bond orientations. The dependency over the orientation of bond arises from the contributions of bond electron tensor component and to the effect of neighboring ions and molecules in the crystals. So a three-dimensional Cartesian coordinate systems comprises three field gradient tensor components, that is Q, ZZ, QYY and QXX. All these are diagonal elements, out of which QZZ is the principal component of field gradient tensor and is in the direction of principal axis of quantization. So these components of fields gradient tensors are used to define eta, or the asymmetry parameter, which is equal to qxx minus qyy divided by qzz, and it varies between 0 and 1. Eta is 0 corresponds to an axial symmetry along z-axis, while eta is 1 corresponds to the two-dimensional gradient effect. So eta is usually described in percentage from 0 to 100%.
The energy level diagram for a spin quantum number of 3 by 2 in the absence of magnetic field and considering the effect of eta is included in the figure, which is shown below. So eta is equal to 0 corresponds to the energy levels E plus minus half lower and E plus minus 3 by 2 upper, and one transition occurs at nu naught. Further, eta not equal to 0 also corresponds to two energy levels allowing one transition. In this case, the quadrupole coupling constant E capital Q into small q changes to account for eta. Therefore, eta needs to be determined for calculating the quadrupole coupling constant from the resonance frequency for any material. So students, you can see a figure showing the comparison of the energy level diagram between asymmetric parameters of 0 and greater than 0 for a nuclear spin of 3 by 2. So for instance, eta nearly 0 for chlorine and most of the organic compounds. The situation is different for inorganic compounds because the relaxation time may be substantial to contribute and provide structural information. Now here comes instrumentation. Students, you can see the schematic of an oscillator used to detect NQR signals. So the instrument works in 2 to 50 MHz frequency range, and the signal from the sample is passed through a differential amplifier that cancels the undesired signal from it. The output of the amplifier drives a lock-in detector which is tuned at the same frequency as the differential amplifier. So the signal from the detector is used as the error signal to lock the spectrometer to a quadrupole resonance. Students, you can see a figure showing the output of the regenerative oscillator detector instrument for 35 chlorine resonance signal of KClO3. So this is one of the example for the instrumentation where one can detect the NQR signal using lock-in detector. So students, let us summarize what we have learned in this module. NMR we have discussed. So NMR can provide spatial information by applying magnetic field gradients. Next we discussed that the application of external magnetic field, that is B, leads to the alignment of magnetic dipoles of NMR active nuclei in S, that is S is equal to 2l plus 1 orientations or spin states relative to the fields. So this alignment is limited by the quantum mechanics. The following conclusion can also be reached from this module, that mu directly controls the sensitivity of NMR experiment, such as the sensitivity increases with a corresponding increase in the value of mu. The local field experienced by the nucleus is B naught, which is not equal to B. It is affected by various electronic factors, that is mainly induction and anisotropy, which control the local density of electrons around the nucleus. Inherent frequency of a nucleus is constant,
whereas its precessional frequency is dependent on B naught. So nu is dependent on the magnetic field B naught. Thank you.